So today's lecture we're going to talk about how to make amplifiers out of a transistor. And we begin with the observation that transistors, like diodes, are nonlinear elements. Basically, the emitter current is an exponential function of the base emitter voltage. That's what's shown here in the picture. As the voltage changes between the base and the emitter, the current on the collector in this case, which is nearly the same as the current on the emitter, grows exponentially, and so it's nonlinear. I will note that in the active region, some things are linear. The current is a linear function of the collector emitter voltage. It's independent of it, and it's proportional to the base current, and it's a large multiple of that. Now, we can treat this linearly, however, if we only consider a small change in the base emitter voltage. So only a small change here means we get a small change here, and we can just take the slope of this line as the function as long as we are only making small changes and we have this linear region. The changes have to be small enough that we can consider it to be linear within that region. So when we do this, we're going to use a small signal analysis where we're going to have large signals that we're going to ignore and small signals on top of those, which are going to be the point of what we want to do. The large signals that we're going to set this up to get it so that things work in the right place, we're going to call those quiescent currents and voltages, and they'll have this little Q value on them. So that's for quiescent. And so how the transistor works as an amplifier will be defined on where exactly we set this point, and that's called the quiescent point. So let's begin with the basic transistor amplifier. So the current on the collector or emitter is a large factor times the base current. And so that's the basis of the amplification of the transistor. And we will want to make small changes in the current so that we can consider it to be a linear case. So we have a case here where we have a common emitter situation with an NPN transistor, and we pick the voltage on the base, we bias it, so that we will get a 40 microamp current flowing into the base. So we pick the voltage and the resistor, so that we get just the right current between this voltage and the 0.7 above ground that we'll expect there. That's how we find the base current. And then we multiply by beta, otherwise known as HFE, which in this case we've made to be 100 in this example. Given that we have a voltage supply on the collector, VCC of 12 volts, we have RC equal to 1.5 kiloohms, and we want to look at the output voltage there. With that all set up, is if we have 40 microamps here, we'll end up with 4 milliamps coming this way. If we look at the collector characteristics of the amplifier, we see here we're in the active region. We've picked VCE 0 to 6 to be 6 volts, so we're right here on the 6 volt line, and we've picked the current to be 40 microamps on the base, so we're picking this line to be the quiescent value, and from that we can read off the 4 milliamp collector current, which is also the emitter current in this case, nearly. The amplification comes now if we change which of the lines here we're looking on, and that's what's represented here. We start with this quiescent value of the current, and we change it up and down by 10 microamps, meaning we pick lines in between the two shown here from 30 to 60, and as we do that, we'll draw more or less current through here, meaning if we draw more current, this voltage will go down. That's given by the load line here. And so if we draw more current, we go to a higher line, the current coming through goes up and the voltage goes down. Likewise, if we drop the current here, this voltage goes up, and we go to a higher value here. So the result of a 10 microamp change in the current on the base leads to a 1 milliamp change on the collector current. Sorry, this should be 1 without a 0. And that is basically because we multiply by the HFE equal to 100 for this particular transistor. And so this example of biasing the base to give this 40 microamps, and the fact that the emitter is directly connected to ground, is an example of a fixed bias. We fix the bias to be a particular value of the current, and then we do the calculation. Now, fixed bias is not the best way to do things for two reasons, maybe more, but at least two reasons. The first is that the amplification depends directly on HFE, the beta of the transistor, and that is not easily controlled. In other words, if you get a batch of transistors from the manufacturer, the gains of each of those will be ranging over a factor of 2 or 3. And what's more, it depends on the temperature. Second thing is that the current that flows as a diode between the base and the emitter is basically like a diode, and it has a reverse current that sets the scale of the whole amount of current that flows. Now, as temperature changes, the reverse current changes, and what's more, the more current will lead to a raise of temperature in the transistor, which will increase the reverse current, the scale of all current, through the transistor, and we'll get yet more current. So as the temperature goes up, we'll get more current flowing through the transistor, which will lead to yet more current, and eventually the transistor will no longer be in the active region. It'll work itself down into the saturation region, and you won't have an amplifier anymore. So fixed bias is not a good way to do things. We want to have something that's more a robust way of making an amplifier. One way to do this is called the self-bias, and that's basically we add a small resistor to the emitter, and we call it R sub E, not using any great imagination in naming that resistor. It's the resistor on the emitter, so we call it R sub E. And that's everything else is the same as before, except that we usually don't have a separate voltage supply for the base. Rather, we use a voltage divider to use the collector supply to also supply the base. That's not really so much the self-biasing. That's a fixed bias. What does the self-biasing is adding the resistor here, which if more current flows through, raises the voltage at the emitter, which tends to reduce the current that comes through, so there's a negative feedback. The resistor divider here can be transformed into the way we expect it, with a power supply for the base and a resistor for the base, just by using Thevenin's theorem. We only look at this part as Thevenin's theorem, actually everything like this. We leave out the transistor and we do the calculation. We find that we have a voltage divider R2 and R1 that gives us the equivalent base source, and that the equivalent resistor there is just R1 and R2 in parallel. And in this case, then we can calculate this for the self-biasing case, what the base current is. And this is true for both of these cases, but we're going to assume we've done the Thevenin equivalent to get these values. In that case, we can find out what the current flowing is by considering a KVL loop that goes from VBB down through the resistor, through the transistor, and finally to ground through RE, and then of course back around to VB. And so we start at VB, and you'll see we have a base current coming through RB, and that gives rise to this factor of RB down in the denominator. You see that if we multiply through, we'll have an RB/IB term. Then we drop through the transistor. That gives us the VBE term. And finally, that base current combined with the collector current, beta times bigger, flows through RE, and that gives us the term in the bottom. And we'll notice that the base current here depends only slightly on beta, or HFE in this case. And so that's how self-biasing works to control the effect of beta and temperature. Okay, so how does one set up a self-biasing amplifier? We actually have a checklist that we can go through. The first step is to pick the quiescent current through the collector and emitter, and we call that ICQ. Q, remember, stands for quiescent, so this is the collector current in the quiescent value. That's the big value of current that's going to control everything else. We pick the value of the collector voltage supply. Often, you're given that. So that's not under your control, and often you're told the collector current as well. Okay, so then you pick a value of RE that's to be such that the emitter voltage is 1/10 of the collector supply. In other words, if we think of the voltage scale going from 0 up to the top, we're 1/10 of the way here, and we pick RE to do that. And knowing VCC and the current flowing, we can calculate what that resistor value is. Knowing this voltage to be 1/10 of that, we know the base voltage should be 0.7 higher than that. That's step 4. Now we have to set up the bias, and so we pick a current to go through R1 and R2. Most of the current is going to go through R1 and R2. And we pick that current to be 1/10 of the quiescent value going through here. And so then we'll calculate what R2 has to be so that that current, I12, that we just calculated, gives us a voltage drop down to ground from VB. So that will allow us to, we know what VB is, and that allows us to find R2. Then we find R1 to complete the, how much the voltage drops here. Finally, we decide where we want the collector voltage to be, and we put that halfway in between ground and VCC. That will give us the biggest gain, or the biggest swing in the gain, because we can have the output basically go from nearly 0 to VCC as we change the current. Once we set that in the middle, we know what to set for RC based on the quiescent current that's flowing. The final step, which is not shown in this diagram, is to put a capacitor in parallel and call it C sub E with the emitter, and that is because at high frequencies we can get a much bigger gain if we let the impedance on the emitter go to 0. That doesn't change your biasing, because the biasing is a DC current, and that will still go through RE, but a high frequency doesn't see RE, it sees the capacitor. Okay, so now we have a biased common emitter amplifier setup following the procedure that we just outlined, and we want to find now what's the gain for small signals. So since we only care about the small parts, we can get rid of the quiescent parts. We forget about them. They only set the scale of the gain, and they won't come into the analysis. We can enforce this by putting capacitors on the input and the output that will block any DC effects going on in the middle from the output. So we put a little signal in there, it makes a little change here and changes what the voltage is there. The voltage on the output will change, but we'll only see the changes in that that come through the capacitor. So the first thing we have to do is find the input resistance of this setup, and when we're talking about these small signals, this will come in. So the input resistance seen from here, what's the input looking into this circuit? It's how much the voltage changes when we change the current. Now, because we're putting small signals in, and we're ignoring the large part, this small change we're actually thinking of as a voltage. A small change in the voltage is the voltage that we're interested in. And a small change in the current, a small change compared to the quiescent current, is the actual current we're interested in. The signal is the small part. And so we use a small letter, but without the D, to show those things. So the input resistance is what you would expect. It's the small signal base voltage over the small signal base current, but it's in fact the rate of change of the voltage at the with current of the diode that forms up the transistor. And so we can just write down our diode equation, take the derivative, and we find that well, we write down what's the current with respect to the base emitter voltage, and that's by definition beta times the base current. Remember, we wrote this down for the collector current. And now we do this derivative, and we find, when we do that derivative, that we get the same thing coming back. The 1 will not be important, so we'll get IC back, but with an extra factor of VT coming out. And so the derivative of the current is proportional to the current that we have, and this is the quiescent value, divided by the thermal voltage that controls how quickly the current grows. If we wrote this instead in terms of the base current instead of the collector current, we get the same analysis, only we had an extra factor of beta in compared to IC, so that the resistance is the base current divided by the thermal voltage. So in this we can replace the change in the large base current with our base signal, small v, and the current with the small I. And so we find when we plug in here that the input resistance for small signals is the gain times the thermal voltage divided by our quiescent collector current. So setting the collector current basically will set the resistance scale for small signals in the transistor. And that's so important that I've written it out here, and I'll put that on every page from here on out through most of the rest of the lecture. The input resistance for small signals depends on the collector quiescent current. It's 1 over that current, and the scale of it is given by the thermal voltage. So it's the thermal voltage over the collector current multiplied by beta, or, which is the same thing, the thermal voltage divided by the quiescent base current. That's the resistance for small signals. I should note that the book often uses different language. They often use R pi for my input resistance, and the beta, the gain, in which case this is the AC, small signal time varying beta, they'll often call H sub Fe, little f, little e, for small signals. So since we're only worried about small values, we can make our transistor model even simpler. It was pretty simple before, but it's even simpler now. We don't care about the 0.7 volt drop anymore because we're wiggling this side, and this side will wiggle too. We don't care if there's a large offset, a large fixed offset in between. Also, because the diode will be set up in a case where the diode is always on, we just remove it. And so we basically replace this with our input resistor that we just calculated the resistance of, and that's the diode that has that resistance. If we make a small change in the current, we'll get a small change in voltage given by that resistor. We still control a much larger current, though. So notice that in this, I've changed all the big letters here to small letters here, so our small signal model will always use small letters. Little I sub little b, little I sub little e, little I sub little b. In this, we calculated, we have a current gain that we've given here. We can also rewrite that in this case as a transconductance, which will be a, we'll have a voltage controlling the current rather than a current controlling the current. This is a current-controlled current source where we have beta, but we can turn it into a voltage-controlled current source with a transconductance G, and we just do that in the normal way because the current flowing into the base is the same as a voltage across this resistor. So if we just do that, the collector, the small scale changes in collector current is beta times the small scale changes in the base current. That's the same as the base voltage, base emitter voltage changing over the resistance. And then we combine the beta and the 1 over Rn to give a transconductance. 1 over R gives a transconductance, and so, well, 1 over R gives a conductance, and it's because it's in a different place, it's the transconductance Gm. So by definition, when we just look at what that is, that's beta over Rn, or IC over Vt. Okay, so we're now ready to analyze this messy system in terms of our small scale model. So we can replace this with a simplified model where we only worry about the small signals. These are small time varying signals. And we're going to assume that all the capacitors in this are negligible, so they all go away. And so we have a number of things. We're always going to, so VC C is a constant, so in a small scale signal that's the same as a ground. We're only worrying about changes from a fixed value. And so VCC and ground are essentially both grounds in the small signal high frequency model. So R1 and R2 are really in parallel. We've already been doing that a lot, but here we can see it explicitly. And so we'll often call that parallel combination R sub P. Likewise on the output, the collector resistor and some hypothesized load resistor will also be in parallel, and we'll call that RO for out. At high frequency, we put in this collector, this emitter capacitor, and that basically gives us a short circuit to ground at these frequencies, so there is nothing on the emitter leg. We replace the transistor with our simple model, and basically that's how we go from this to that. So now we can find the gain. We're going to assume that in this calculation that RS is small, and that the input resistance is much smaller than R sub P. So in that case, what goes into the, so that the current that flows into the base, which means not flowing down this way, but flowing into the base, is the V sub B, which is V sub n over R sub n, because that's connecting it to ground, so it's easy to see. And then we plug in the value for Rn, and we get this value for I sub B, Vn times the quiescent value IC, beta, and the thermal voltage. To find out what IC is, we just multiply that by beta. That's given by our current-controlled current source, and so that just kills the beta here, and we have Vn times IC, the quiescent current, over the thermal voltage. So now what's the output voltage? Well, if that current is coming up, it has to come from ground through RC, RL, so that gives us a minus sign, minus IC times RO, this resistor. And plugging in from IC, we get this, or we could use this value. So now I want to find V out over Vn. I just have to divide we have to divide Vn out of this, and I get that the gain is the quiescent current times the output resistor divided by the thermal voltage. So everything in my gain is basically going to come from how I set the quiescent value of the collector current, and the scale that makes everything work is the thermal voltage, and then what my load and collector resistors are will also be there. But I can also state that in terms of the gain is beta, what the transistor does, by the ratio of the output resistance to my input resistance. So this is an easier way to think about it. I have two resistors, one on the input, one on the output, and I'm going to get a gain out of those, sort of like our inverting amplifier. But the whole thing is multiplied by beta from the transistor. We can do the same kind of analysis for an emitter follower. We take this and we replace it with a small signal model. Again, we're going to assume that the source is much smaller than the resistor. That basically just means we'll have to add them together anyway. And so we will, in this case, I've just turned things around so that my collector is down here and comes from ground, and so the output voltage here, which is just VE, is the current from both of these sources flowing down through here, so that current determines this voltage. But that's just 1 plus beta times the base voltage flowing here, because this controls that. And then V in minus V out is just the base current across R in. And so I can then expand that, plugging in V out here, moving it to the other side. I find that the input voltage will give me a certain current based on this when I plug it in. And then I divide out I take V in over V out to find this. So I have the IBs will cancel, and I have 1 plus beta R naught, and then R in plus 1 plus beta R naught. I can divide out the 1 plus beta R naught here, and I get 1 over 1 plus R in over 1 plus beta R naught. And then I can plug in what's the value for R in. It has a beta as well, so I have beta over beta plus 1 over my quiescent values and thermal voltages and things I set up. So notice the gain here does not depend strongly on beta, and in fact it should be close to 1 as long as beta is pretty big. Now we had a very simple model for the transistor. We can make a more general model that we will use occasionally, but it motivates why we have the names we do. In this model, there are 4 things you can do with the transistor. There's a current in and current out, voltage in and voltage out, and in this case, the input voltage and current is the base, and the output voltage and current is the collector. This is because in this model we're always talking about the emitter, the common emitter case, so it's always connected to ground. It's not independent. Now, of those 4 parameters, we're going to pick 2 to be independent and 2 to be dependent. And the independent ones are going to be the current into the base and the voltage out of the transistor. And the other 2 are dependent. And so we can write what is the output current, and it's some function, which we just take to be a Taylor expansion, right? We say the current changes with the input current at a fixed voltage, and it changes with the output. It changes the output voltage at a fixed current. So we can vary our 2 input parameters to see what the given output parameter is. Notice this is by definition a linear system because we've only taken the linear terms of this expansion, and we've neglected everything else. We've also gotten rid of all the constants because we're not concerned about those whenever we have little letters. So we can call this parameter, we'll call it HFE, and we'll call this parameter HOE, this parameter HIE, and this parameter HRE. So I should explain that naming. This is the H parameter model, that's why they're H's. The E in the subscript in every case stands for emitter, common emitter. So this is for the common emitter. So the F stands for forward. It's the forward gain in current. So if I have a given input current, I get an output current so many times bigger. That's a forward direction. Forward meaning going this way. I have a reverse gain on the voltage. So if I change the voltage here changes, being pushed back in a reverse sense. HIE is the input resistance, and it actually gets a resistor. And we also have an output conductance. And so those are the four parameters. And given what the units have to be, we can make this model of it. We have an input resistance, right? It's a VN over IN, so it's an input resistance, which we just draw there. Now the voltage on the input has this other voltage gain, voltage over voltage, so we write that as a voltage source. Likewise, we have a current gain, so we write that as a dependent current source, and a conductance given the fact that we want a current out for a voltage in, HOE. So the typical values for these things, the gain for HFE, the gain for that is 400 to 40 to 500. That's why we often use the value of beta of a 100. Input resistance depends on the current. Remember, it depends on the quiescent current, so we have to set it, but we'll typically have values so HIE will typically have values in the kiloohm range, so 1 to 15 kiloohms. That's given that we have 5 to 15 volt sources, voltage sources on the collector, and we'll use and we'll want milliamp currents on the collector. The output conductance is typically measured in micromhos, and the reverse voltage is typically very small. So again, we have already been using the input resistance and the gain, and there's just two more parameters that we might consider. So in this model, we can do the same things we did before. All we have to do is plug a more complicated model in for our transistor. Everything else is the same. And so again, we can calculate V out. V out is the current that flows through here. I'm going to still neglect HOE because it's very small, and HRE is going to be 1. Or is going to be 0. So we're still only going to have those two components. These are going to be neglected, which means a short circuit there, and this will be gone, no conductance for that path. And so we just restate the gain we had before in terms of these new parameters, and before we had beta over the resistance, the input resistance, we just relabel that as HFE over H sub IE.